Templates in C++ are extremely powerful. They're probably my favorite feature that the language has to offer, and I know a lot of senior game developers would agree with me there. If you are a beginner to C++, you've probably only used templates at a surface level, but you are really missing out. Templates can greatly reduce the amount of code you have to write so you can make faster progress. They can reduce the amount of bugs you have due to copy pasting code because you're reusing a lot of boilerplate code. They can greatly increase performance in some situations. They can greatly reduce the readability of your error messages and increase compile times. Wait. The good news is that error message readability with templates has gotten so much better in modern Visual Studio and with C++ 20 concepts, and the compile time bloat can really be reduced through a few techniques like extern templates and precompiled headers, and these are things I'd go over in a future video or you can look at on your own. If you're a beginner, then templates can maybe seem a little daunting. They can definitely get a little bit hard to read sometimes when they get complicated because, complicated code tends to look complicated, but it is easier than ever to learn templates. Modern templates are so much easier to use than they have been before, and we have LLMs now that can really help you parse that stuff. They're actually really quite good at it. So I'll give you an overview of templates with some practical examples and some examples from my game engine, and then in future videos we can go a little deeper. A common thing to want to do in games is to prevent a number from going beyond a certain range. Like say we have a Pong game and we want to make sure that our ball can't go outside of the arena. Maybe the arena is at 0. Then we could do this, ball x is less than 0, then it becomes 0, right? Or if it's greater than 32, then maybe ball x equals 32, something like this. This is a common pattern. We want to make this reusable. Now, there's a way to do this automatically. You can use std clamp, right? And you can use that function. We're going to make our own clamp because maybe we don't want to include algorithm or maybe we don't have GLM or something like that. So let's make our own little clamp function. Now, this is going to return an integer because ball x is apparently an integer. So we'll call it clamp, and then int val, int min, int max. And then we just, copy paste this and change all the numbers around. And of course, since we're clamping to min and max, we want to use less than or equal to or greater than or equal to. Okay, so what's the problem here? Well, clearly we can clamp this. So if we call clamp, right, like ball x equals clamp of ball x, maybe to 0, 32 like we had before, and we can see out this ball x. This is gonna work, right? It's gonna clamp it to 0. But what if we decide, ball x is a float now, okay? So ball x is a float, -1.f. When we compile this, what's going to happen is we're going to get a warning. And if you're smart, you have turned on compiler warnings as errors. I highly recommend doing that. It is really important. So here's our error. Warning has been treated as error, argument conversion from float to int, which of course, this is an integer function. Now, obviously, we wouldn't want to go, okay, let's make float clamp, right? And then just do every single different version, because then maybe we want to use uint16, maybe we want to use vector2, something crazy, right? Good news, that's what templates are for. Templates actually do this sort of generation of all these different function definitions for you. So let's change this to be a templated function. To do that, it's really simple. All we do is write the word template, and then we get these little angle brackets. These angle brackets are where we put special template arguments that basically define what are the things that can change. What are the things that you can just arbitrarily put in? So you usually put something like, you'll either write type name or class. Both are going to be the same. I'll use class, I guess. Class T. And now this T can be used to replace any type in this function. So we can put T for all of the ints like this. We could also use multiple types if we wanted to. If we wanted a function that could have one specific type in the first argument, one specific type in the second argument, we could go like class N. You can also give the, instead of using class, you can say a specific type of thing. Like you can say int in, and this will be a literal integer. So we could actually, instead of passing in max here, we could pass it in as a template argument and literally generate code that has the max hard coded. But we're not gonna do that. Let's do it just class T like this so you can see what happens. So right now we're getting an error. And the reason for that is it can't figure out how to build our template here. We have float and then integer and integer. The reason for that is these need to be floats, right? So now it's going to compile, it's going to work for float, and if I was to change this back to an integer and just make it -1, we get that same error because then these are floats, right? And these need to be integers. So one thing you can do to make this a little easier is to do what I said, where you have multiple different template arguments. So we could have class U and then class V. So we can just be super arbitrary and be like, you can pass in whatever the heck you want. So you'll have one type for val, one type for min, and then maybe one type for max, like this. And what we can do is anytime we're doing these comparisons, like in the function, we can just cast to t. And there are times where this might break down, like if you're using really weird types, like maybe a glm vec2 or something like that, it'll give you a compile error, but this will work for us now. So what I can do is I can go back to float like this, and this will just work because inside the clamp, even though this is a float, an int, and an int, you can see when I mouse over it, it's generating a function float clamp float int int. And this just works. So this is a templated function. There are also templated classes, and it does the same thing. It's just doing a replacement of a type with whatever you put in. Additionally, like right now, you'll see I didn't have to do anything special here. It just deduced what types I was passing in. It knows that ball is a float. It knows that these are integers, so it knows what to actually use. But you can actually explicitly tell it what to use. Like I can put int, int, int here, and I can say use int for these three types. This will go back to probably not compiling again because ball x can't be converted to int because it's a float. So then I would have to do this. There are times where the automatic template deduction won't work for you and you'll have to use this. For example, std vector. If you say std vector, my vector, this is invalid. And template classes in general are going to be like this. You have to tell it what type you want it to be. In this case, we could say vector integer, right? If you go to vector, you can actually go to the definition, and you can see there's a little bit more like verbosity here, but they're just doing the same thing. Template class underscore t. This is the type, and they also have a second one here, a second parameter that you can optionally use. You can see it's already set to something by default, just like a normal default parameter. This is the allocator for the vector. So this is how the vector decides to allocate new memory. You can actually make your own allocator classes to replace the vector's inbuilt allocator, but by default, it'll just use whatever allocator is for this type. That's obviously really powerful. You can come in here and say, hey, I want my vector to actually use like memory arena allocation or pooled allocation or something like that. And you're still using the vector implementation, but it's generating different code for you that uses different classes. Now I have gone ahead and moved our clamp function into its own little utils namespace and its own little utils file clamp.h so we can include this everywhere. And obviously this is useful to do, but I've also done this because I want to illustrate something really important. So hopefully, as you know, generally you want to avoid having a lot of code in a header file because every single file that includes that file is then going to be redundantly copying that code into their translation units and then recompiling it. So you actually end up bloating compile times the more code that is in a header. That's why we create CPP files and we move the definitions of the class into CPPs and keep the actual declaration of the class or function outside of the CPP. The problem is that's not something you can easily do with templates. Now, what's nice is if we're not using the template in a file, like say we have this clamp function here and we're not using it, nothing's going to be generated. Like in main.cpp, we're only going to generate right now a integer definition with, or I guess a float definition with two integers. But if we were to, in main, for example, call this again with different types of arguments, we would then generate another version of that function. You have to keep in mind that we end up generating a new function for every single different combination of these types that we have. That can also bloat compile times. You're not just getting one nice clean clamp definition, you're getting n definitions where n is the number of different ways you've used the class. If you keep using the same argument types over and over again, then you're going to obviously be able to reuse those. And the fact that we can't easily move these into the C++ file is going to increase compile times. But let's see why we can't do that. So if I just try that, if I just take this and I put it into the CPP file, okay, so I already set up this utils thing right here. We just move that down. Here's our definition. And then up here, we just put a semicolon here and just say, okay, here's our class declaration. If I try to compile this, this is not going to work. So there's our error, link error, unresolved external symbol, blah, blah, blah function. So it can't find the actual definition of the function. In main, where we're trying to use this, it doesn't seem to know that this exists. And the reason for that is that templates work by generating the code sort of in line. The main function, whenever we include that clamp.h file, remember includes are literally just copy pasting this. All main is seeing is this. It doesn't actually know how to generate the function. So we have to put this in the header file. Now there are ways to do this in the CPP file. So what we can do is basically create that instantiation that we're looking for that main can't seem to find because it's not being generated here. There's nothing in this CPP file that's asking for that float int int generation, right? If I mouse here, it says float int int. So let's do that. What we can do is explicitly instantiate that float int int implementation in this CPP file. So we need to tell the compiler what to generate so that the linker can actually find the thing. So what we can do is do what's called explicit template instantiation. So we'll say template here, and then we have our return type, which for this is, I believe, a float, and then clamp, and then we have our 3 arguments with template parameters. So float for t, int for u, int for v. Let me double check that. Yeah, int, float, that is correct. And then we close it off with the actual arguments in parentheses. So again, float, int in this case. So here, and then we can put a semicolon. So here is our explicit specialization, or explicit instantiation, not specialization. So IntelliSense is complaining, but ignore IntelliSense. It doesn't know what it's talking about. So now when I run and actually compile, this is going to work. So it's actually finding, the linker is able to now find this function definition here because it's being generated in this CPP file. Just like you would normally have declaration and a header and a definition of the CPP, that's what's happening here. So I showed you that it is possible to put the definition in the CPP file and the declaration in the header file, but you really shouldn't do that, because when you do that, you kind of lose the benefits of templates, where anybody who just wants to use that function or class can use it with whatever types they want, or at least types that fit what it's supposed to do. So instead of trying to define it in the CPP file, just put it in the header file. What we can do is use what are called extern templates instead to make the compilation much faster. We can actually guarantee that there's only going to be one definition of any given combination of these template parameters, instead of potentially having duplicate definitions over different includes. So anytime you're using a template class many times throughout your code base and you're using the same parameters over and over again, this will help you speed up your compilation times. We don't want to duplicate those definitions, right? We want to have just one. So we type extern template in the header, and then you put, your normal, the same as we did with the explicit instantiation, you put the template arguments you want for your specific class or function. So here we'll do what we had before, float, clamp, and then float. This is an annoying example, I'm starting to realize. Int, and then float, int. And basically we just move this into the CPP file too. So we copy that, put it here, and then just get rid of extern here. What this is doing is it's telling any CPP file that includes this header that, hey, if you're trying to use this specific series of template arguments for this specific function, don't actually generate a version of this. Like, don't do that. The linker is going to give it to you later, because I promise it's defined somewhere else. And we are, in fact, defining it in the CPP file right here. So once all of our includes are included, they're not going to be generating anything duplicate, and then the linker is going to link this single definition of the clamp function for all of our usages in all of the different files. And you can do the same thing for a class. We can say class my class, right? And it can have template type name T or class T. You'll see both. A class, I think, is the more modern way to write this, but they're effectively the same thing. And then you just do the same thing. You would say extern template class my class, and then, I don't know, float or something, right? And then in the CPP file, you do the same thing. So we would grab this part and put it right here. And there we go. Now our compilation speed is going to be much higher. I use this for a few things in my engine that are just used a whole lot, and it did significantly improve the compile time for those things. And maybe this is like, we'll call it like magic array, okay? Maybe we're doing something special and we want to have like a specific array in here of data in this class. And what we can do is also include integer in here. And maybe this is going to just give us an array of n. This is like a bootleg std array, right? This is not very good, but we can actually do this. Now I can write functions that use this data, and you'll see, because this is a static sort of array data, this is essentially, like I said, a bad std array. We can use that here. So we can say like magic array, my array, right? And just like with vector, we have to give it parameters. So maybe this is an array of floats, and maybe there's 64 of them. So now this is a stack allocated array, and it's in the util namespace because that's where I put it for utils. Another cool thing we can do is what's called explicit specialization, and it's different than instantiation. What specialization is it allows us to actually say, in specific cases, the definition of something is slightly different. So we can say here, say we want to make clamp do something weird if you pass in, I don't know, a Boolean. Maybe we want it to just like print out hello if there's a Boolean parameter. We can do that. So the way we do that is we type template here, and then we say bool clamp, right? And then we put bools for the arguments. Bool val, bool min, maybe bool max. We can also template some of these if we want to. And then here I'll just say cout hello. And what's happening is this is overriding the normal definition of clamp with one that is specific to bools. And there's times that you want to do this. Sometimes you have a very interesting sort of template setup where certain classes need to have a little bit different behavior when they are used inside your function or class, and this allows you to do that explicitly. So let's run this and see if we actually get that with some booleans. So I'm going to just cast these to bool, like the bootleg way to do this here. Bool 32 totally works. Ccasts just kind of work, right? Cout is not a member of STD, so we need to include our string. Must return a value, so return false. My array, unreferenced local variable. Delete you. So I'm getting a multiply defined symbol link error. We can fix that by putting inline here or by moving this into the CPP file. This will work though. So let's try that again. And then finally we should compile and run. There we go. So now I hit a breakpoint. So we have called clamp, and clamp is now doing cout hello instead of doing what it would normally do. Now I want to talk about performance a little bit. Because templates are actually generating code, they can allow you to inline things that you normally wouldn't be able to do. And let me show you a really good example of that. So let me get rid of all this stuff. I've already went ahead and built this template performance test here. It's going to do some timing measurements for us to test some things. The way this is built is we have this template tests file, and it's setting up everything for us. The situation is we have a tile grid, okay? It's a grid of tiles. Maybe we're playing chess, or maybe we have like a game. It's a really big world where, you know, it's like an RPG where you can move tile to tile and battle enemies or whatever, right? You're going to want to sometimes do things to those tiles, let's say. Let's say it's a very common thing in our game to want to loop through all the tiles and just do something to them. Either print them out or modify their HP or something. Right now they have like ID and an HP, just a stupid little tile struct here, right? Well, there's different ways we can actually do that. The sort of manual naive way to do that is in this test right here. So we have a vector of tiles that we get from the grid. So when you go to the actual tile grid, you see internally it has this vector of tiles, and then it has a size, and this can be pretty big. In our manual one, what we're going to do is we're going to set up our timer. We're going to get all the tiles, and then we're going to loop through all of the tile coordinates. And then we're going to do something. We're going to call do thing, which does just some math to the health, completely arbitrary. This could be whatever you want, right? But we're going to just like subtract the health, whatever. Just trying to do things to make the optimizer not like ignore things. And then we're going to increment the total health. Again, we need to store this because I'm going to be running this in release mode, and we want to make sure that the compiler doesn't optimize things out. If you actually end up printing things out, that'll stop the compiler from optimizing them. And then we're going to track how much time elapsed and then return that. So then we can measure how slow was this thing? How slow was it to loop through all the tiles, do a very small amount of math. This is pretty cheap math right here. And then add a number, right? Let's see what that takes for a bunch of values. So right now in main, I have this set up to do 3 different types of tests. We'll start with the manual one, which is the one I just showed you. So I'm going to build this in release mode, and we're going to see how fast it is. So I just ran our test in release mode. We have a grid size of 2,000, so 2,000 squared tiles, quite a few tiles. And then we're doing 20 tests and averaging the results of those tests. And we get an average of 22 milliseconds, not very long, to do that iteration and do that simple thing over all of the values. So that's all well and good, but one thing we don't like about the way this is set up right now is that if we go to template test.h, this pattern here where we have to get the tiles from the grid and then manually loop through all of the coordinates and then do our thing, that kind of sucks. We have to copy paste this, like the comment says. If we're doing this a bunch of different times in a bunch of different parts of the code, we're copy pasting this. That's a bunch of extra code that we don't really want. There's opportunities for us to mess this code up, or for the way that tiles should be iterated to change. Maybe the orders of the tiles change or whatever, and now we're iterating it the wrong way, right? It would be really nice to be able to say, hey, tile grid, can you just do this thing to all of your tiles? So that's what the second version does. This is the function for each test. And you can see this is much, much smaller. This is calling a function on our grid called for each tile, and it's using a lambda function to just pass in the stuff we did before, calling do thing, incrementing total health. We're passing total health in as a reference to that lambda, so we have that. And then the function itself is going to give us the tiles and the x and y coordinates. If we go to the definition of this, you can see now the actual tile grid itself is handling what it means to loop through all of the tiles, and then we're calling our function. So let's try this version. So I'll change our test type here from manual to function, and we'll see how much faster or slower this is. So remember, before it was about 22 milliseconds on average. Now our test runs, And oh, now we're at 51 milliseconds. What happened? Well, the problem is std function has overhead. Not only the function call itself having overhead, but now that we're using std function, we can no longer like inline the code. It has to do an actual function call, push a new frame onto the stack, right? And std function itself also has quite a lot of overhead. Now we could have tried to use just a straight up function pointer instead of std function, but then we wouldn't have been able to pass in this total health like this. We would have had to somehow get it in there as an argument. Maybe it's like a void star or something way slower, but we like this. This is really nice to write. Is there a way to get this nice to write thing and still have it be fast? Yes, that's where templates come in. So finally, we'll go down to the last one, template for each. And you can see it's exactly the same. This code, template for each, and function for each looks exactly the same. The difference is that we're calling this for each tile templated. And if I go here, you can see here's the normal for each tile, and here's for each tile templated. The normal one takes an std function with our specific arguments. The for each one takes just type name func here. This could also be class func, right? And then it calls func. So this is a template parameter that is whatever we want, but we're going to be treating it as a function. Obviously, because it's a template, we could like call it with like an integer and it would just crash, it would just not compile, right? It wouldn't work. And in a future video, I'll talk about templates where we can make sure, or I'll talk about concepts where we can make sure that this is the exact type of function we want with a nice clean error message. But for now, we're just going to use it as is. Let's run it now with the templated version, and you will see that we get the best of both worlds. We are now back to the maximum 22 millisecond performance, but our code is much easier to write. And there you have it. It went up to 24 milliseconds. That may just be noise, but it is still extremely fast enough for you to want to use this. So as you can see, templates are very powerful for generating code. They can actually speed up certain patterns that you want to use. Now, I wrote this in a particular way on purpose so that you could maybe think about how we can even make this better than it already is with templates in terms of the test itself. So we have these if statements here. We're checking for each type here, and then we're doing, these internal function calls here. But when we go in here to each of these, if we actually look at what's going on in each of these tests, the function for each test, the manual for each test, and the template for each test, most of the code is actually the same. We have the same 3 lines down here. It's printing stuff out. We have the same stuff here at the top, right? So we could try to extract this stuff into maybe functions and call the functions instead. That would maybe work here kind of, but there's a potentially even cleaner way we can do this using templates, where we have a single test function that switches out what it does in the middle based on the test type that is defined up at the top here. So I'll restructure it and I'll show you what that looks like. All right, so I've rewritten it now. It is much smaller. And what you can see here is instead of having these 3 if statements here, right, these const if statements selecting which implementation, we now just have one implementation called run template test. And I'm passing in what type of test as a template argument. You can see this is a constant template. This is a constant template test type up at the top. Because it's constant, we can pass it in as a template argument, like directly into the angle brackets. And then we just pass in our grid size as normal. When we go here, we see that we have basically moved those 3 if statements inside. So based on what this test type is, we are doing one of these 3 different things. And an important thing to note, these are compile time if statements. This if const expr means it's going to be evaluated at compile time, and it's going to, there's no actual runtime cost. The different instantiations of this are going to literally be like copy pasted, just like we had down here, right, with different implementations for each of them. But instead of having to scroll down through all of this code and make sure, oh, if the tile grid's interface changes, we have to change all 3 of these interfaces, right? Or if we change how we do timing, I have to change all 3 of these places. Now there's just one place that I have to change, and the only branching on implementation is happening where the implementation actually differs, right? It's really nice. It's also just really nice to be able to look in one place and see all of the different behaviors instead of having to scroll through the whole file or go to different functions. Now I'm just going to show some random practical examples. Not going to go into the full details of how all these things work, but these are actual classes from my game engine. So for example, here is a RollTable class. It's a template class, takes a single argument. The point of this is it represents a table of things that you're basically going to roll dice to decide if you get that thing. So a really good example is if you're rolling to get item drops from, killing a creature or something like that, right? So we just use T for the inner actual object that we're storing. and then, a quantity of the number of things that we want to get as a result. And then we can set our probabilities and everything the same for any different type of object that we want to actually roll on. Like, we don't really care what is in the table that we're rolling on. We care how the roll table works, and we want to be able to use that for whatever. I want to roll on ints, I want to roll on dragons or creatures or whatever items, I can do that. And then here's an example. I am using Extern Template because in my engine, I know I'm using this for items. So I have an extern template here. Right now, I think I only use this for items. So let's look at a much more complicated example. Very practical though. So let's say you're making a game, you're gonna have assets. At least you really should have data assets, not just pure code assets, right? Like, you want to be able to save things to disk that represent your game, like materials, textures, models, all of these things, so you can actually build your game without recompiling it every time you want to change something, right? So here in my game engine, we have the animation montage def. If you're familiar with Unreal, Unreal has animation montages. This is pretty much based off of that. If you're not familiar with that, just think of it as a very fancy way to do animations where they also have extra data attached that you can use for like VFX and gameplay triggers and things like that. And you can piece a bunch of animations together into one of these things to basically make an ability. Now, what we want to do for any asset in our game is to actually be able to modify the asset in editor with widgets and sliders and things, right? We want to be able to change these different blend out durations. We want to be able to check and uncheck checkboxes for these Booleans here. And when there's more complicated sub assets or sub objects, we want to be able to render the controls for those things and have it just work without having to manually write the actual like mGUI rendering function for every single asset that we make. Any object, really. Like, we want to avoid as much manual writing of that repeated code that we could really just auto-generate. We also want to be able to save this thing to disk and load it from disk, right? Because you need to be able to actually change the asset in editor and save it so the next time you launch the editor, it's still there. And so you can actually ship it to your players. And again, don't want to manually write all that stuff. We want to generate that. So through the power of both templates and macros combined, we can actually achieve that. So here in the header, I have this verbose little declaration here. Pro tip, if you're in Visual Studio and you want to like see how a macro works, like see how the actual text replacement is working, you can mouse over this and click expand inline. That'll make a nice little like just expanded version of that. This is the actual code that's being generated by that macro. And you can see that that macro I added there is just giving us these three functions: write, read, and draw mGUI. So just like I described before, this is writing to a YAML string, basically a YAML node, so that we can save that to disk, and then read is doing the opposite of that, and then draw mGUI is doing the actual imGUI rendering in editor so we can mess with things. Now that's the header file. That's just saying basically these things are defined, you can use these things, so our editor can call that, right, to actually do the thing. But as far as what's actually generating all of that stuff, it's this magic pile of stuff here. So it's another macro, right? And you can see we have these different make field definitions in here. And these make fields are actually overloaded to allow additional information. Like, I can say blend in for a nice fancy editor name. I can give minimum and maximum values like this. So that the slider itself that is generated for this control has those minimum and maximum values. I just haven't set it up for this asset because it's kind of in progress. But what we can do again is expand inline, and this one's going to get a little messy because there's a lot more going on. But here's our write, read, and draw mGUI that we saw before, right? So let's try to maybe clean this up like a little bit. But you can see those make fields that we put in there are kind of copy pasted between all of these things. So we're basically describing the data in each of these different functions, and each of these functions in turn calling a templated function. So you can see, it's kind of hard to tell here, but the write function is calling YAML serializer serialize YAML fields, and it's taking a template argument of the actual asset type, and then it's taking the big list of all the things inside the asset. So if I actually go to this serialize YAML fields here in the actual header where this is defined, you can see this is using templates, and it's using what are called like variadic recursive templates. It's basically a template function that you keep calling itself with each further and further argument. So each of those elements in the make fields that represent the different values, like if I go back, these values here are just these values right here. So you basically just have to specify these in the CPP in that declaration. Each of those gets called in its own serialize YAML fields function recursively, and then this knows how to put that value into the YAML string just because the value itself will have had a definition already defined for how it can actually serialize with this operator. Similarly, the draw mGUI also has a draw mGUI function. This is going through the YAML serializer, but it calls into separate mGUI util draw function, or draw mGUI function here. And this again is a templated function that takes any control, and then it checks a bunch of different common things. So you can see we have those if const expers like we did before. So instead of doing like template specialization, which I could have done for some of these, I'm just using a bunch of if statements. And remember, these are compile time, so it's fine. So like floating point values, right? It's going to generate a slider. Or if it's a Boolean here, this is a compile time check for is the type a Boolean. Do a checkbox, really simple. Integer sliders, we have strings, we have custom vector types with different vector inputs here. We have like color types here, and then we have a bunch of extra stuff down here, which some of these could be collapsed into, to be honest, which are these special things called concepts, which I'm not going to go into in this video, but you can see like this concept is called has free draw mGUI, and what it's looking for is there a function that exists anywhere in visibility of this that is called draw mGUI that returns a Boolean that takes this type. Or there's different ones, like has mGUI with range. Is there one that takes a range? Is there one that takes a label? And these if const expers are just checking, like, does this function exist somewhere? If it does, we're going to compile with this instead. So it's going to then call that draw mGUI function. And if you remember, that draw mGUI function was actually generated by our little declaration here, right? That this is the draw mGUI that's being called there. So we're recursively using templates to call functions that in turn use templates, right? It's a lot of layers of templates, but you end up with something that with just one quick macro, and then just specifying your fields, and then if you like these make fields, like I said, are overloaded, right? So you can add a lot of custom configuration into these if you want. These actually create an object for us called a YAML field. And it just has a bunch of information, like I can disable IMGUI for a control if I want to. I can change the label. I plan to add like flags here for like behavior flags. Like maybe I want to actually change the way certain controls behave. That can also be added here, right? Again, just a template. A certain type of object, right? This T exists in this field, and then it has some attached like metadata, right? So I know that was a lot. We went from the very beginnery stuff in templates to the very advanced stuff. I don't expect you, if you're a beginner, to have understood everything I said, but it is easier than ever to learn templates because, like I said before, we have LLMs now, and there's just so much information on the internet now about how to use these things. So you can literally like take all this stuff, copy paste it into ChatGPT 3.0 or whatever, and ask it to really explain it to you line by line, and make sure you actually understand it, right? It is good to, use the LLM to generate things that you don't always understand, but then you want to make sure that after you do that, you like actually read what it's telling you and ask it to elaborate if you don't get it, because you want to be able to really accurately describe what you want when you're trying to generate templated code, either by yourself or with an LLM, right? If you don't really know what you want, you're not going to really get the right results because you just don't understand it. So thank you for watching, everyone. Check in the description. We've got a Discord now. We've also got another channel that you can check out for more specific game development videos about the game we're making. And stay tuned for future videos. Let me know if there's anything else you guys want to see. After making the video, I realized I forgot to actually show off the mGUI control generation in editor, so I'll do that. So in our editor, we do have all these asset editors for all the different assets. Anything with a button that's blue has an asset editor created. And creating asset editors also uses templates. I won't show that now, but it makes it really easy to make new asset editors and generate everything you need. So I'll open up the animation montage, and we'll go to error attack right. So I cleaned up some of the fields, but you can see on the left, here is that auto-generated IMGUI controls for all of our stuff. We have blend in, blend out. We have upper body, root motion, all these different things that were all in that animation montage def right here. All this stuff, right? Anything that can be drawn that has a draw IMGUI function defined will just be kind of added here. And I even have the ability to do arrays. So like if I create a new just random segment here, and this is like breaking the animation a little bit, but you can see I've added a new segment to the animation montage, so it's playing two different animations back to back, right? And they show here in this array, or this vector view. And I can add and remove them here. I can move them around. I can do all these things, and it's all just generated for me. I don't have to write any additional code. Just makes it super duper easy. So highly recommend doing something like this if you're making your own editor. This is something that if you're working in Unreal or Unity, you're probably used to because they do this for you. And if you're not doing this in your own code, you're really missing out again.